Hi everyone. So in today's video, we are going to go over this paper, Lookback Lens, detecting and mitigating contextual hallucinations in large language models using only attention maps. So this is by people from MIT and UWash, and I found this paper to be really interesting. And I'm also going to present this to like an internal reading group. So I thought, why not also record this thing as a practice run and upload it to my channel for others to go through. This is a fairly recent paper. This is still a preprint, I believe, and it hasn't been published at some venue, but I believe it might be under review because the template looked like an ARR style template. Yeah, but moving ahead. So, what exactly are hallucinations? So, content that deviates from facts or contextually relevant information. So, saying that someone is, say, for instance, it says Elon Musk is the president of the United States, while that is not true, or it has some context with respect to which we expect it to give an answer. So maybe we wanted to answer based on a news article, but the model deviates from that. So all of those are hallucinations. And this acts as a significant challenge in the deployment of LLMs because if you can't be sure what the model will say for a particular query, you don't really want to put this out on the web, right? So, what are contextual hallucinations? So, if you remember, the title contains this word contextual hallucinations. So, what are those? So, LLMs can hallucinate with respect to many different things. Contextual hallucination is when it creates details or unsubstantiated answers which are inaccurate with respect to the input context. So maybe the input context said, summarize this given piece of article, and the model summarized it, but it converted the facts to something which is not true or something which is not present in the input context. So in this paper, they focus on the scenarios where you give the model correct facts within the input context, but still the output is not accurate. So some of the tasks they cover are like that. We'll go over that soon, but at a high level, this is what contextual hallucinations are. And then these are some statistics for evaluation. So for instance, CNN DM is a summarization task. You have 1,000 examples, and you see that Llama 2 7 billion chat only got 49.6% correct. Like when they judge using GPT 4.0, which is another discussion altogether whether you should judge by LLMs, but I think almost everyone is just using LLMs to judge. So the rest had some form of the hallucination or other. NQ is another natural questions task where you need to answer based on uh, some context given. So in their case, we'll go over this later, but in their case, they feeded some Wikipedia pages as context from the data set apart from irrelevant pages. And then there you can see that it has 67.8% success. So that means something like 32.2% was still being hallucinated. So what's the prior work like? So let's see what's the difference first. So in like most prior works, they focus on the model uh, parametric knowledge. So that means that something which the model has already encoded within its parameters, and they want to see whether the model hallucinates with respect to that or using that. But in this work, you want to see what is the hallucination like with respect to the input context. And what do prior works use? They use things like hidden states, MLP outputs, attention block outputs, attention head outputs. So all of these basically some kind of the other hidden state to build classifiers for hallucination or use them to figure out a classification boundary for when can you use what does a hidden state look like when the model is hallucinating, sort of. And another thing you might be interested in seeing is when did these works come out? And you can see almost all of them came out in like the last year or so, at least by like the works which this paper cites, and you can see 23, 2024. So this is a very fast moving field. Now, what's like a high level overview of the state of hallucination research? So in their case, so in this paper, they refer to contextual hallucinations, but previous papers have defined two kinds of hallucinations, closed book versus open book. So closed book is where basically the model does not have any context and it needs to rely on its parametric knowledge, while open book is knowledge is given in the context and the model needs to use that. So in this paper, this open book hallucination is referred to as contextual hallucination. And then most prior works also treat detection and mitigation as two separate tasks. So one thing is to figure out whether there is hallucination, and another different thing is to actually reduce this hallucination. While in this paper, they use the detection method to build a tool which they can use at inference time to mitigate contextual hallucinations. So some observations which this paper builds on. So the provided contextual information plays a key role in detecting contextual hallucinations because you're going to use that as a point of reference to see whether the model hallucinated. And then attention is much more meaningful than, say, the hidden state output of the 30-second layer of some lava model, right? Because you can sort of visualize attention as how much weightage did the model uh, put at this time step on each of the preceding tokens. So they speculate some stuff based on this, but this is what motivates them to use only attention maps. And since prior works had already looked at other model internals, they felt that attention maps might be the logical next step. So what is their hypothesis? They want to leverage signals from attention maps, and they hypothesize that if a model is hallucinating with respect to the context, that means the model is not putting enough attention on the context. So the model keeps generating tokens, and as it generates tokens, it pays attention to what was there in the context, as well as it pays attention to what it generated during its earlier time steps. So if the model does not pay enough attention to the context, they speculate that this might uh, be causing hallucinations. And then they create this feature called Lookback ratio, which is basically the ratio of how much weightage of attention weights was put on the context versus on the newly generated tokens. And then since at each time step you recompute these things, they calculate the lookback ratio for each attention head because each attention head operates differently and train a linear classifier on these lookback ratios. So they use some annotated data to train a classifier and then use it to test. So first, let's look at attention heads for people who might need a refresher on this. So I won't go over the entire transformer architecture, but these are some visualizations from the illustrated transformer blog by Jay. So it's an excellent resource, and I would highly recommend reading it if you're confused. So usually you have input X, and then you project it using the query key and value matrices to get your query key and value. Then you do this softmax to get your attention weights. And then this is basically the entire attention thing if you have only one attention head. But in practice, you have more than one attention heads, like 8, 16, something of that order. Larger models have even more number of attention heads. So for instance, if you have two attention heads, you will have two separate uh, weight two separate sets of query key and value matrices, one per attention head. Then again, you will compute these attention head scores called Z. So you can just have, like, suppose you have 8 different attention heads, then you have all the way from Z0 to Z7. And then you concatenate all of these, you multiply it by another projection matrix, and you get Z. And this is what is then sent, created. This is what is passed on to the feed forward network, which is also present in a transformer block. So usually you have attention and then feed forward network in like the original transformer setting. And this is like the entire picture. You have a sentence, you embed each word. So thinking and machines become two different words. Then you split it into, suppose you have, if you have 8 heads, then you multiply X with each and every of one of these matrices, Q, K, and V. For each of those heads, you get a query key and value for each of those heads. Then you apply that softmax thing which we saw. So essentially this formula, and then you get a score for each of them. Then you concatenate them, and you then multiply. So you concatenate this, you multiply it with a projection matrix, and you get your final Z. And then, yeah, this is basically a refresher on attention heads. If you find this a bit confusing, you can also refer to the original blog or other videos who have covered attention in much more detail. This is not the intention of this video, so I will skip over. So let's formalize what we want to do now. We want to compute this look back ratio, but how do we compute it in practice, or what all things are we using? So take a transformer with L layers. Each layer has H number of attention heads. You have input sequence of N tokens. So this is your context. You generate T minus one tokens, and then now you're generating the Tth token. So you have N tokens of context, and you also have T minus one tokens, which you generated, which are now in context, but it was not there originally. This is something which the model has generated. And then for each time step T and for each head, so each head has its own attention patterns, you calculate the ratio of attention weights focused on these tokens in X versus those in paid on these tokens in Y. So let me also pull up the equations. So alpha HIL. So this notation basically says you take the Lth layer, H attention head, and then the ith token, and alpha LHJ is basically uh, the softmax attention weight assigned to yth token. So basically the jth token in Y. So you can look at this. You have all of these attention weights assigned to these tokens. And then basically the average for context is you just take an average over these n tokens of context, while you have t minus one tokens of generation. Each of them has this generation, each of those tokens in context, each of those generated tokens also has attention weight, and then you average over that. And then you can just compute the look back ratio as the aggregate attention on the context divided by the total aggregate attention. And then this is also for a given time step, layer, and attention head. Some more formalization. Now, how do you use these ratios? Because you have one such entry for every layer, head, and timestamp, right? So let's first aggregate them for a particular timestamp, and then you get this vector VT, which is basically all different layer head combinations at a particular time t. Now you can also do this for multiple generations, because you'll need have one for yt plus one, and all the way up till some capital T. So basically t plus t minus one is the final token for them. And then you also correspondingly get all of these VT vectors. And then you aggregate them. So you take a mean position wise. So you basically take LR11T, same T plus 1, all the way up to T plus T minus 1, average them across this dimension, again an average across this dimension, and so on, and you get one vector. And finally, you train a simple logistic regression classifier to predict if the span is factual or hallucinated. So they take factual to be 1 and hallucinated to be 0. And you can see this is simply a weight transformation plus bias, and then they use a sigmoid activation. So this is a very standard logistic regression classifier. So again, this is a visual depiction of the same thing. So in your attention, multi-head attention, you have these attention maps. This is this is lower triangular because you apply a causal mask. Essentially, you do not want to show the future tokens to the model at older time step, so it can only attend to the tokens which the model has in context right now. It cannot use the future tokens to sort of deduce, okay, what should I predict at time t by, if it already knows what's there at, say, t plus 5, it can make a much better guess about what should be at t, or it totally spoils or ruins the causal language modeling objective, because in practice you won't actually have that. So these are x1 to xn are your context, y1 to yt minus 1 is the generation. You average over x, you get this, you average over y, you get this blue block, and then this is your ratio. Now you have h heads, l layers, and t tokens in a span. So you have h cross l uh, number of entries in each of these vector, and then you have t of them. You average over t, you get this one vector, you pass it to a linear classifier, you get the probability of it being hallucinated or not. So I hope this part is clear. So this is what they call as the look back lens. And now you might wonder, okay, so we haven't yet decided how to pick up a span, right? So you take this given text span of interest, but you don't really know what is, you haven't really defined a text span of interest just yet. So there are multiple ways to define a span. So in this paper, they look at two of them. So one is have predefined spans. So if you have these annotations for hallucinated and non-hallucinated spans, you can directly train the classifier to differentiate between them. So you can always sort of take everything which is going to be hallucinated as one and something which is not hallucinated as another kind of span. But in practice, you rarely have these annotations. So they use also test with this sliding window. So here you do not have a predefined span, but you have a fixed size. So they process the sentences into fixed size chunks. In most of those their experiments, they use a chunk size of 8, but they also do some ablations with other chunk sizes. And then they train a classifier to predict whether any hallucinated content is present in the chunk. So maybe half of the chunk is hallucinated, half of it is not. They will still take that chunk to be hallucinated. And then annotated data is only used for creating labels and not for span segmentation. So the spans might be half hallucinated, only 1% hallucinated, and so on. And then, so in the predefined span setting, so for the sliding window, it's pretty clear how you'll build your spans. You'll always have like these fixed size spans. But in predefined settings, they have span setting, they have three kind of span. So one is the text segment before the first hallucinated span. So this is all non-hallucinated. Then text after the last hallucinated span, all of that is also non-hallucinated. And the response annotated as non-hallucinated. So anything in between as well. And then all the annotated hallucinated spans, so it might be of different lengths, are used as negative data to train the lookback lens. So, and in the sliding window setting, they consider all possible fixed size chunks with size 8. If a chunk is overlapping with any of the annotated hallucinated spans, then it is hallucinated. So I hope the span setup is clear. In terms of the model, they use Llama to 7 billion chat. For some future experiments, they also use Llama to 13 billion, but for the first part, they use this model. They do greedy decoding till 256 tokens or until end of sentence is generated. And then they use two data sets. One is the CNN DM, which is a summarization thing, and the other is natural questions, which is Q&A. And then for annotations, they use GPT-4o. So they want to judge how truthful the model is and also to mark how much hallucination did the model produce. So for doing this, they use GPT-4. And so this is a part which I'm sort of sad about in terms of how our field is moving. This is not just this one work, but in general, stronger models are being used to evaluate smaller models, but we really need to fix this. Yeah. So they do this small studies on 70 samples of summarization and they get 96% consistency, but this doesn't mean a lot, right? You have only 70 samples, you only use one task. So you can see the problems. These are some examples from the datasets of CNN DM is where you have this large article, and then DM is basically Daily Mail, and then you have these highlights, and your task is to basically generate this summary. And the natural questions is a much bigger thing. So you can look at this document. You can see this is a lot of HTML, right? So this is the entire wiki page for The Walking Dead. Then you have this question: when is the last episode of season 8 of The Walking Dead. Then you have the answer. Basically, you know in what indices in this document does the answer exist, and basically you have a reference answer. Your task here, at least how hallucination works formulate it, is they give the model three documents with the gold document in the middle. So that gold document contains the answer, and the other two are irrelevant. And then the model needs to pick up the correct answer. So if it hallucinates, it can hallucinate because of not picking the right answer from the correct document or from focusing on the incorrect document altogether. And this is a much more challenging task where you have questions from real users, and some Wikipedia answers pages may not even contain the answer, so that is also a possibility. Finally, they use GPT-4 for their labeling, so you can see they have these prompts, and uh, some some of you might be interested in how they do the evaluation. They have these prompts where they give the model some examples and some instructions, and then they ask it to reply in a particular format. So you can see all of these are just prompts. So what baselines do they compare against? One is a text-based entailment classifier. So NLI is a very popular and long-studied task where you basically need to tell whether two sentences are in contradiction to each other, are entailment, or are not related. These are usually the three classes in NLI. So they fine-tune a DeBerta model for the same, as well as use a state-of-the-art entailment model, which is also a DeBerta model, but it was trained on like 730,000 or something NLI data points. And then they also you compare to previous work by building this hidden state-based classifier. So they use 24th, 28th, and 32nd layer representations. Now the results. So this is the result table. They use the area under the ROC curve metric. And let's just go over like some findings from this work. So if you look at the look back lens, you can see it underperforms on train to some degree because the hidden state classifier seems to overfit to it, but on the test set, it is on par, if not better in some cases. Like for instance, it hasn't overfit as well as it hasn't overfit as much as this. So it is still overfitting. There is a difference, but the authors say that it is overfitting less, which I mean there is some justification there. And then this is basically if you train on QA and if you test on QA, you get this score, and if you transfer, you get 85.3 on the summarization task, which is lesser than say what you get on the same domain, but it is still better than what other hidden state classifiers got. While for the state of the art things, they are much lower, the NLI tasks. Similarly, this is for predefined span, and then for sliding window 8 again, you have similar trends. So on sliding window 8, you can see the train loss is much, the train like AU rock score is much lower here, as well as the test on the same thing. But if you look at the transfer task, it is again much better. So it seems to be generalizing more than hidden state based classifiers. But on the same domain, it seems to underperform, especially for the sliding window thing. So it achieves better performance than the SOTA and fine-tuned NLI models. It is you can see the utility is more significant in sliding window settings, and I guess they say this based on the transfer scores, which are like 7% higher than even the max 59.4 here. And then hidden state based classifiers tend to overfit during the twofold validation. And once you go out of domain, they have a sharp drop. So you go from 100 same domain test to get 11%, 10.4% drop, and then you here get like a 20.6% drop. So this is now the results so far. So these are classification tasks where you need to predict basically they have gold data for whether something is hallucinated or not, whether some span contains hallucinated content or not, and these are the scores. They do not report any other metric, which I find a bit weird. Why not report like macro F1 or um, accuracy? Macro F1 seems like a better score because you have some sort of balancing and a skew if you just because you'll have much less portions which are hallucinated and much more number of things which are just general English, which is not hallucinated. So reporting that might make a lot of sense. Maybe they will do that in a future update of the paper. And then look back lens guided decoding is basically, if you remember, I mentioned that they use this to not just detect but also mitigate. So they use this lightweight classifier because this is just a simple logistic regression classifier to create a decoding method where at each time step, after like a few time steps, when you generate a chunk, you see which of those you generate multiple chunks and then you see which of those have the lowest hallucination score sort of and are much more faithful to the context. So basically, you generate, in their case, size 8 chunks. So you generate 8 tokens and then you generate 8 such candidates. You get their ratios, you get scores, and then you pick the one with the highest score to get your uh, output chunk. So this is how your when you pick this, you basically concatenate the previous chunk with the new chunk, and you keep repeating this until you get the end of sentence. So this is just a formally written version of this. This is an example. Suppose you have this uh, document about Beyonce, and then if you just do greedy decoding, you will see that it misrepresents the earnings which Beyonce had. You can see that Beyonce's earning are uh, she played in 95 shows, bringing in an average of 2.4 million per city. So if you just do the math, this is like 180 million, 190 plus million, 200 million, something of that sort. But this sort of just constructs something from this 64 million and this 100 million. It just is totally wrong. While if you use their decoding, you can see that first it picks up this chunk. According to Forbes, Beyonce had the biggest year of her career in terms of. So you can see this at the start, it had these two which had sufficiently high score, but this had the highest score. So the decoding method will pick this. Then it will generate some things which are like truncated here. And then towards the end, you can see uh, these things where it has like a new number or a wrong earning mentioned, it gets a very low score by the classifier, while this thing gets a very high score. So this becomes the next continuation. So some of the experiments, they use the XSUM, the natural question answers, and this empty bench task. So XSUM is basically a summarization. They take 1,000 samples and then evaluate using GPT-4o on a binary scale, whether then NQ is basically again natural question answers, and they evaluate the best span exact match. So basically, they want to see whether you extract the correct spans. And then for multi-turn conversations, there's this empty bench data set where they pick up 80 samples, and the model needs to produce a second turn response. And GPT-4 is then asked to score on a 1 to 10 scale based on all of these factors. So one interesting thing I noted is that they mentioned GPT-4 here, but I guess this is GPT-4o because it would not make sense to use a different model for evaluation in one setting while all the others use GPT-4o. So again, they train look back lens on a summarization data set and then use on these three tasks. Baselines is just greedy decoding and then creating other classifier guided decoding. So what if we use an NLI model to see how how much hallucination was there and rank the responses or use a hidden state based classifier. So the results you can see here, the original greedy decoding you can see had 49% correct. So this means that 510 examples were hallucinated While if you look at this 58.6% correct, this means that you had 404 hallucinated. So it's an 18.8% reduction. This does not mean that this solves the problem, but this is like a next step in this direction. And you can see this is higher than most other things except SOTA NLI, and it is still very close to it. So the state-of-the-art NLI is trained on 731,000 examples. So they speculate maybe having a classifier which is trained on a higher set number of examples would be better. You can see for NQ task, it matches the state-of-the-art NLI thing. And then for empty bench has two things, so two subtasks. One is the hallucination and one is the original thing. So on both of these, it beats everything or matches uh, at least the best. Then, yeah, we already discussed this. And then it can also boost performance on the hallucination setting, so for instance, when you did redecoding, you had 6.08, which means that 70, uh, sorry, 93.92% were hallucinated. This is a small increase, I guess, but it's still an increase in their language. And I'm not sure what kind of difference it would make for 80 samples. Is probably like one or two sample difference. Now for cross-model transfer, so what if you train this thing on one model? Can you transfer it to another model? So basically, if you train based on the attention head weights of one model, do other models respect it? So they do not do this very extensively. They only compare between Llama to 7 billion chat and Llama to 13 billion chat, and they do not want to retrain it. They only basically train on one model and pass it to the other. Now, there is an issue here. There are 1024 heads in 7B while 1600 heads in 13B because you have more layers and you might also have more heads per layer. I'm not sure about how many heads per layer each of these have, but it's certainly a large difference, right? So you somehow need to map them between the two heads, the two models, each head. So how do they do this? They extract the average lookback ratio per head for all the D training examples. So you have 1024 cross D matrix for the first one and a 1600 cross D matrix for the second one. So you basically have how much attention ratio per head per data sample in this matrix for both the models. Then you fit a linear regression model to map the heads to reconstruct the 7 billion thing from the 13 billion thing. So you basically train a linear classifier to a linear regression model to go from this matrix to this matrix. And then once they have learned this transformation, you can apply this transformation to the look back ratio from 13 billion and use that for the 7 billion classifier. So this is what they do in their cross model transfer. And as for the results, cross-model transfer yields slightly worse results compared to same model transfer. So if you train on 13 billion and test on 13 billion, you go from 84 to 60.4, 84.3 to 60.8, and then 93.3 to, oh, sorry, this is the score on, sorry, two different settings. So, but still you're training on 13 billion, testing on 13 billion. While if you train on 7 billion and test on 13 billion, you get worse scores, but it's still not like trivially low is what they claim. So you can see it's like at least in this example, say for sliding window summarization trained and then testing on QA, you can see it's just a 0.03 difference. So I'm again not sure on how much do these area under rock curve scores mapping, how much are they mapping to say macro F1 scores. I'll love if the authors can update the paper with that, but this can give you like a overall gist of what kind of scores do they get. And then you can also look at some cross-model transfer on the decoding task. So the first thing is the detection task, but now you have the decoding task. So you use if you use the greedy thing, you get these scores which we already saw before. If you use the SOTA NLI thing, you get these scores. If you train on 13B and test on 13B, these are the scores you get. While if you train on 7B and test on 13B, these are the scores. So in some cases, it even outperforms everything else, right? And it is still fairly close. Like it's a 1 to 2 point difference across all of these. So cross-model transfer also seems to work well. Now, cross-model plus cross-task at the same time might be hard. So they do a cross-task thing as well, where uh, they do a setup where there is no cross-task. So basically, you don't train on summarization and test on Q&A. So this is basically this setting NQ train to NQ, and these are the results. So these are higher here, is what they're saying. And this is also not different tasks because both of these are summarization tasks. So these also are close by to uh, their results for greedy and state-of-the-art NLI. Now, some ablations. They look at the chunk size. So if you remember, we only looked at chunk size 8. They look at chunk size 4 and 16. So for some reason, they uh, only mention the greedy score for chunk size 8, but then you can look at their scores and they say that for some tasks like natural questions, the look back lens seems to prefer a shorter chunk size, while for things like exam, it prefers a longer chunk size. But in general, the improvements are consistent across different chunk sizes, and you don't really need to optimize your chunk size. One of these values should do. Then, how much predictive powers do different heads have? So what if you only take the top 10, top 50, top 100 heads with the highest correlation? If you use all heads, you get 85.3. If you use the top 100 heads with the largest magnitude, you get 82.8. So you don't quite recover the entire performance, but even with a smaller number of heads, you can close in the gap. So they basically use the coefficients in the linear classifier as a proxy. Top 10 is much worse, and increasing K, of course, increases the performance. They also look at if what if you pick the most positively and most negatively correlated heads only. So I think I messed up the title, so this should be 1 out of 2, and this should be 2 out of 2. But I hope you get the point. And if you look at only the most positive top heads, it performs much worse. If you look at the most negative, it performs much worse. So you seem to need both to use both the top positive and top negative, or like both the positively and negatively correlated attention heads for getting a getting a good prediction on whether something is being hallucinated or not. Okay, I think I had an extra slide there. So again, heads with positive coefficients have higher look back ratio. So they have higher factuality and less hallucination, supposedly. And then heads with negative coefficient suggest a lower look back ratio. So they attend more to the generated tokens. So they say that this corresponds to being truthful to the generation, I believe. They do not explicitly mention truthful to what, but I believe it's like you generate more coherent things and you're truthful in that sense. But this is something which I'm not super sure about. What do they mean here? And then this is their basic hypothesis that negative hits are probably more responsible for ensuring consistency in its own generation. And for that, you need to attend to the generated tokens. You can't just keep looking at the context and write coherent English. And now, what if you reduce the number of layers? So, how about using only attention heads from a particular layer? And you can see that it seems that it is not concentrated in any given layer. However, layer 13 to 16 and layer 17 to 20, so the middle layers, they seem to be the closest. Uh, and some layers, like if you only use the start or the end, it performs much worse. but it still isn't that if you use only one layer, you can one set of layers, you can recover your entire performance. And finally, I think this is the last slide I have for this paper. Yeah, this is the last slide I have. So I think this covers it all. I really found this paper to be very interesting. Love if the authors can like update it with some additional results for other metrics. But overall, I hope this was relevant to you as well. Thank you guys for tuning in. Hope to see you again next time as well.